Hello everybody. This video is going to be a continuation to the previous topic, and in this video we are going to start the discussion on the losses in case of turbulent flow. But in the beginning I'd like to start this part with a more in-depth discussion on the turbulent flow in internal turbulent flow, and to understand how the velocity profile varies from laminar to turbulent and what are the implications of this. So as we said before, that the turbulent flow is the more common type of flow that we use in our engineering applications. And as we said before, also that the study of the flow types or the fluid flow is not an easy thing, and in order to do this we have to have some assumptions so that the equations can be derived. And this is what we did when we derived the Poiseuille equation. And as we saw, it was for a very specific case. And for other cases, if for instance we have non-Newtonian fluid, or we have non-circular pipes, or any other different assumption, this derivation is not going to work, and we have to do more complicated derivations. So even for laminar flow, it wasn't an easy task. It was a very special case that we were able to do the derivation for. So for turbulent flow, it's even much more difficult to do this. So we cannot do what we did in laminar flow for turbulent flow. Turbulent flow, one of the reasons, or the main reason, is that the turbulent flow is very chaotic flow, meaning that by chaotic I mean the at specific point the flow velocity and direction cannot be predicted easily. So there is a random motion of the liquid. It's going in what we call eddies, is like swirls, that the fluid is making while it's moving forward. This is a very useful thing, because these eddies are what make the transport of heat and mass, or energy and mass, more enhanced in the turbulent flow than in laminar flow. So this is why, as we said before, that we do the design, or when we design the equipment like heat exchangers, like distillation columns or separators or whatever, we make the design so that we make sure that the flow is turbulent. So this is something that we do on purpose. Otherwise, the equipment that we are using will require or will have to be with very large surface area if it's heat transfer equipment, or with a very large size if it's a distillation column, to achieve the desired heat and mass transfer thing. So I mean, this is something, I think I mentioned this before, that laminar flow looks much nicer than turbulent flow, but doesn't mean that turbulent flow is a bad flow. Turbulent flow is a very useful flow for us. So now let's go for the velocity profile. So the velocity profile that we are very familiar with since the beginning of this course is this parabolic velocity profile. It has zero velocity on the walls, or near at the walls, for the no-slip boundary condition, and it has a maximum value at the center, and it takes this parabolic shape. Okay, so this is what we know. For turbulent flow, it has a very different velocity profile. And this profile is very intuitive if you just think of it from a pure conceptual point of view. So we know that the turbulent flow is a flow that has high inertia, and this is because Reynolds number is high. It means that the inertial forces are much higher than the laminar or the viscous forces, so the fluid can flow with high inertia. So the viscous effects, which is the effects of the friction between the fluid and the walls of the pipe, will only affect the fluid closer to it, while the fluid in the center, which is far from the wall, will have high inertia. It's not much affected by the whatever is happening at the wall, and that's why it has this almost uniform velocity profile at the center. So this is the simple logic. I mean, this is has nothing to do with the equations or anything. And this is what happens in reality. So for the laminar flow, if we take a look at the velocity profile, you'd see that the velocity is changing from the wall where the velocity is zero all the way to the center of the pipe. So the velocity change over the distance change is not so big. So the velocity is changing over very large distance, which is the radius. So this is what happens in laminar flow. For turbulent flow, if we zoom into this place where the velocity change is taking place, the figure that we have here, this one is the one to the right here. This is an exaggerate. It's not an exaggerated. I mean, it's just for demonstration, but it's not to scale. So if we see the actual velocity change, it's happening at a very, very, very small distance. And there is a very big change in the velocity in a very, very, very small distance. This distance can be 1% of the radius. So if the velocity in these two cases is the same, the maximum velocity, and this velocity is changing over the whole radius, this velocity is changing only in 1% of the radius, so this velocity or this gradient is 100 times the gradient here. Okay, so it means that there is a huge change in the velocity over a small distance. There are some, and of course this is, as I said, it has to do with the shear stress between the fluid and the walls, and how it's affecting the fluid at different distances from the walls. So this is what's called or the shear stress at the wall is called the turbulent shear stress, and there are some models that have been developed to predict the shape of these models. I'm not including them here because they're just models that are based on different assumptions, and I don't think there is one of them that is a model that's approved by all the scientists in this fluid mechanics community. So it's good to know, but I don't think this is important to discuss here. So to understand the shape of this velocity profile, there is a kind of a theoretical what can I say? It's a way of describing the fluid or putting the fluid as different layers from the wall to the center of the pipe, according to the forces acting on them. So we have this viscous layer. So this is the layer that is adjacent to the wall of the pipe. So this is the one that is very, very or touches the wall and the few layers adjacent to it. So this is 100% affected by the viscous forces. So the friction is affecting this layer directly, and that's why you'd see the velocity profile here is a linear profile, as it looks in the laminar flow. So it's you can consider this viscous sublayer as a laminar layer. So it's 100% affected by the viscous forces. On the other hand, the part at the center and around it is called turbulent layer. So this layer is far away from the wall. It's not affected by the viscous forces by any means, and it's 100% affected by the turbulence of the fluid or the inertial forces of the fluid. So this is the exact opposite of this. There are two layers here that are called the buffer and the overlap layer. So it's kind of a transitional layers between the viscous sublayer and the turbulent layer. So the buffer layer is a layer that is highly affected by the viscous forces, but there is some effect of the inertial forces. That's why you'd see it's not linear as the viscous layer is. It starts to take this curvature here. For the overlap layer, the viscous forces become less less obvious here in this overlap layer, and the buffer and the inertial forces are more dominant than the viscous forces. So it's more like a turbulent layer with a small effect of the viscous sublayer. So these are the layer. This is, of course, this is not actually what happens. If you can zoom in and go inside the pipe and see how the fluid is flowing, you cannot see this classification of the layers. But it's good to understand this or have this idea of how the friction forces are affecting, or the viscous forces are affecting the fluid velocity, to understand the velocity profile. So now if you look at the viscous sublayer, it is, again, we mentioned this before in the beginning of this chapter when we were discussing the entrance region, and we said that the entrance region, there is more pressure drop or more fluid energy loss in the fluid than the fully developed flow, and this is because the velocity change is very high over small distance. And as we said, the thickness of the viscous layer is almost 1% of the whole radius. It means that the velocity changes from 0 to a large value in a very, very small distance. Just to have a feeling of the numbers, if this radius is 10 centimeter, then this high or change in the velocity happens in only 1 millimeter, which is a very, very small distance. So it means that the change of the velocity with y or with distance is large, because y is very, very small, and this means that the shear stress at the wall is going to be very, very high compared to laminar flow. Okay, so this is the message that we have to take from this, that the shear stress at the wall, and consequently the energy losses in case of turbulent flow, would be larger than those in case of laminar flow. To have a good or more understanding or idea of how the velocity profile or the thicknesses of different layers in this velocity profile can be or are calculated or estimated, there are some models also in the textbook. You can check them. Again, there is none of them that is verified by everybody or agreed on by everybody. And also, this is a kind of theoretical thing that is not going to affect our calculations for the head losses in case of turbulent flow. So I don't think it's going to be very, very relevant here. So it's in the textbook. You can go and check it if you want. So this is all for the this video. Inshallah, in the next video we are going to start the actual calculations of the energy losses and how the pressure drop can be calculated for turbulent flow. So I'll stop here and we'll continue next time, inshallah. Goodbye.